Okay. So this is tutorial 3, which is mostly about normal shocks. So in this set of video solutions, I'm going to use the formulas to solve problems. So mostly these things. So what you see here, this is the isentropic flow relations. This is the normal shock flow relations. And down here is for the last question. It's fan line flow relationships. Okay. Yeah. Okay. So in the previous few videos, we've seen how to use this. Okay, so I'm not going to go through this that much. Let me introduce you the isentropic flow relations. So basically, they are formulas that relates the 2 points before and after the shock. So remember that we have a shock, right? Upstream of the shock, we label this as point 1. Downstream of the shock, we label this as point 2. So you see, all the 1s and 2s here pertain to these 2 points. So T1 pertains to the temperature at point 1. T2 pertains to the temperature at point 2. P1 is the pressure at point 1. P2 is the pressure at point 2. M1 is the Mach number at point 1. M2 is the Mach number at point 2. Okay, so this is what these symbols mean. Okay, so look at this function, for example. This relates the two Mach numbers together. So you see, the Mach number at point 2 is purely a function of the Mach number at point 2. Okay, it's also a function of K, but K is, for our problems, right, we're mostly dealing with air, and air, K is always 1.4. Okay, so we can forget about K because most of our problems we use air, so it's always 1.4. But you see, other than K, right, the only other variable is M1. Okay, so that means once you know M1, you can definitely find M2. Conversely, once you know M2, you can definitely find M1. Okay, so that's very useful. Okay, so if you know the value of one Mach number, let's say you know that this is 1.5, then you can use this formula to calculate M2. Okay, so very simple. Once you know any of the Mach numbers, you can find the other Mach number. And once you have both Mach numbers, right, once M1 and M2 are known, okay, both of them are known, then if you are given a condition on one face, on one side of the shock, you are able to calculate the condition on the other face of the shock. So let's say P1 is given. Okay, this is given, this is given, this is known. Then you are able to use this formula to find T2. Okay, find. Okay, and likewise for temperature too. Okay, so this may seem very abstract, but don't worry, you will understand what I mean when we go through these questions. Okay, so without further ado, let's get started. Question 1. Air flows through a converging duct. Okay, so let's draw out the problem. Air flows through a converging duct, and a normal shock stands at the exit of the duct. Okay, so we have a shock here, and label the upstream and downstream points of the shock. Downstream of the shock, we have the Mach number of M3. So this point is labeled as 3, and Mach number is 0.54. Okay, notice that this is subsonic, right? And remember what I said, behind, or should I say, downstream of the shock, it is always subsonic. Okay, if the pressure ratio upstream of the shock, and then that at the entrance is, given to be this. So this is 0.2, and up here is 0.1. Okay, the pressure ratio, okay, so we're given that P2 over P1 is equal to 2. Okay, so calculate, okay, so compute the Mach number at the entrance. So find M1, and also this area ratio, A1 over A2. Okay, so A1 over A2. Okay, yeah. So let's go ahead and find the Mach number at point 1. So we're given this shock, right? What do we know about the shock? Okay, you see, we know the Mach number on one side, right? So that means we're able to find the Mach number on the other side. Meaning, say, we can immediately find M2. Okay, so let's go ahead and use the formulas. So which formulas shall we use? We shall use this one, the Mach number formula in the shock relations. Okay, so remember these are shock formulas, right? So between point 2 and point 3, you must use these sets of formulas. Okay, so let's go ahead. Okay, but now we're not dealing with points labeled 1 and 2, right? Now we're dealing with points labeled 2 and 3. So how do we apply this formula? Well, you simply replace 2 with 3 and 1 with 2. Why? Because in the formula that we are given, right, this 2 refers to downstream of the shock, downstream, and this 1 refers to upstream of the shock, right? So you see who is upstream and who is downstream. Point 2 is upstream and point 3 is downstream. So that's why we replace M2 with M3 and M1 with M2. Okay, so let's go ahead and use this formula. So I'm going to directly apply that formula. So remember, M3 is M2 right now. So replace that with 0.54. That's the given value that it gave you here. Okay, squared is equal to M2 squared plus 2 over 1.4 minus 1. Okay, so this looks complicated to solve. You can solve this algebraically, but let me show you how to do this with a calculator. So let me share my screen. Okay, so on the left-hand side, we have 0.54 squared. Yeah, and then on the right-hand side, right, we have the gigantic fraction. So what you need to do is move the gigantic fraction over to the left-hand side. So you get minus that fraction. The unknown is m2, so we just labeled it with x plus 2 divided by 1.4 minus 1, 2 times 1.4, 1.4 minus 1, okay, x squared minus 1. Okay, so now you plot this out, and what you do is you find the zeros of this graph. Okay, so the zeros mean the root, the place where it cuts the x-axis, which is here. Okay, I know there's another 0 here, but you can ignore it because Mach number is always more than 1. Sorry, Mach number is always positive. Okay? There's no such a negative Mach number. So you see, here we found that the Mach number is 2.25. Okay, so let's go ahead and write that down. Okay, so we found graphically that M2 is equal to 2.25. Notice that it's supersonic, and we expect that to be so, right? Because immediately upstream of the shock, it should be supersonic. Okay, so now, how do we find the pressure ratio, right? Oh, sorry. We also want to find... Okay, yeah. Let's find the pressure ratio first. Okay, so... Sorry, we are given... Okay, so sorry, I was confused in my train of thought. We are given this pressure ratio, right? So how do we find this pressure ratio? Okay, another way to express this pressure ratio, right, is this. So let me write this down and I'll explain to you what I'm doing. This P2 over P1 can be rewritten as P2 over P0 times P0 over P1. Now, why can I do this? Okay, let's take a look at the flow between 1 and 2. What kind of flow is between 1 and 2? This is considered an isentropic flow. Okay, this is considered an isentropic flow. You see, the hint says here, the flow from the entrance to the point upstream of the shock can be considered isentropic. We are told that is true. Okay, so once you know that the flow between 1 and 2 is isentropic, you know that for isentropic flow, any 2 points on an isentropic flow share the same stagnation conditions. Okay, they share the same stagnation pressure, they share the same stagnation temperature. So, having known that, I can rewrite P2 over P1 as P2 over P0 times P0 over P1. Okay, P0 is the stagnation pressure. And why is this mathematically valid? Well, you can see that okay, if you were to simplify this fraction out, this and this can cancel, leaving behind P2 over P1, right? Which match the left-hand side. But how do we know that this exactly has the value of this? It's because 1 and 2 are 2 points on a isentropic flow. And isentropic flow share the same stagnation pressure. That's why this P naught will share the same value, okay? Yeah, so that's the logic of why we re-express it like this. Okay, so we are able to find this, okay? We're able to find this. Why? Take a look at the formulas here. See, we have P naught over P at any given point. Okay, P naught over P at any given point. I know right now we're dealing with the upside down of that, so we're given P2 over P naught instead of P naught over P2. But let's stick with this formula. Okay, let's stick with this formula that we see here. Okay, and apply it to point 2. Okay, so if you apply that formula to point 2, you have P naught over P2 is equal to 1 plus 1.4 minus or 2 times the Mach number at point 2, which is what we found. Okay, if you press this in your calculator, this will be 11.64. Now, you may ask me, well, how do we get P2 over P naught instead, right? This is just the upside down of this. In other words, P2 over P naught is the reciprocal of P naught over P2. Okay, so in order to find P2 over P naught, what we do is P2 over P naught, we just take the reciprocal of this answer that we found just now. Okay, so 6, 4. Okay, so if you find this reciprocal, punch in your calculator, you should get 0.085891. Okay, so you see, we managed to find this. Okay, and we are given this, right? Remember, we are given this pressure ratio to be 2. That's given in the question, right? See, given. Okay, so that means we are able to calculate for this unknown, right? This right now is unknown. So let's go ahead and do that. So P2 over P1, I'm just copying down that equation that I wrote just now. P2 over P naught times P naught over P1. Okay, so this one is 2, which is given to us. This one is this value, which we found just now. 0.085891 times P naught over P1. Okay, if you solve for P naught over P1, you will get 23.2852. Now, how do I use this to find the Mach number at point 1? Okay, well, we can use, again, this formula, except we now apply it to point 1. So let's go ahead and apply this point 1. So the formula says P naught over P1 is equal to 1 plus 1.4 minus 1 over 2 times the Mach number at point 1, which is unknown, squared to the power of 1.4 over 0.4 minus 1. Okay, so this value is equal to this, right? It's what we found just now. So you can go ahead and make that replacement. Yeah, so replace this with the 23.2852 that you see just now, and then you realize that your only unknown is M1. So if you solve this equation, M1 will have a value of 2.7. Okay, so this is correct. Now let's find the next thing that they want, which is the area ratio. Okay, so how do we find the area ratio? Well, you see, keep in mind that, again, 1 to 2 is an isentropic flow. And what's another special thing about isentropic flow? Not only do they share the same stagnation conditions, they also share the same critical conditions. Okay? They also share the same critical conditions. In other words, they also share the same critical area. Okay, so points 1 and point 2 share the same A star. Okay, so we're gonna make use of this fact to calculate A1 over A2. First, let us re-express A1 over A2 as this. So I'm going to show you the re-express form and then explain. Okay. So see, A1 over A2 can similarly be written as A star, A1 over A star times A star over A2. You see? let's see mathematically why is this true. So these two can cancel, leaving behind A1 over A2, right? Which is what we get in the left-hand side. Now, let's see why is this true from the point of fluid dynamics. You see, why is this necessarily equal? It's because point 1 and point 2 are 2 points on the same isentropic flow. And remember, 2 points on the same isentropic flow share the same critical area. That's why this value is necessarily equal to this value, and they can cancel. Okay? And it just so happens that we have formulas for these individual fractions. Okay? We have a formula for this, which is given by this. Okay? And likewise for A star over A2. It's just the reciprocal of that, right? So let us go ahead and find the two individual fractions. So A1 over A star, right, is given by that formula. So I'm going to apply that formula where you replace the Mach number with 2.7, which is what we found just now. Okay, so you will find that the first area ratio will be about 3.183. Now, let's find A2 over A star. Okay, so remember Mach number at point 2 is 2.25. This is what we found earlier. Right? So you calculate this, you will get 2.10469. Okay, but we don't want A2 over A star. We want the reciprocal. We want A star over A2. So how to get the reciprocal? Well, you simply take 1 over this answer that you got here. 1 over 2.0469, and that will be about 0.475. Okay, so finally, we can calculate A1 over A2 by taking this answer times this answer, right? That's what this says. This answer times this answer. So 3.183 times 0.475, you'll find that you get 1.512. Okay, so this is the correct answer. Now let's move on to question 2. So question 2 says that air with stagnation conditions this and that accelerates through a converging diverging nozzle with a throat area of this. So let's draw a converging diverging nozzle whose throat area AT is equals to 0.0019 in meters squared, so it's already in SI units. A normal shock occurs where the area is 0.038. And what is the Mach number before and after shock? Okay, so here is the stagnation condition. So I'll label this as 0. We have a P naught of 1034.21 kPa. And T naught, change it to kelvins, you shall get 477.44 kelvins. Then what else? Okay. Okay, so the question is, where is the shock? Is it in the converging section or the diverging section? Okay, so that's a question. Because it could be the case that here, right, has an area of 0.0038, and here also has an area of 0.0038. The question is, where is it? Okay, and there is a correct answer. Okay, it's one of this. So the correct answer is that the shock occurs here. Why? Okay, so remember I said that you need to remember the structure of a shock. That is to say, you must remember that if the flow is in the rightward direction, you must remember that immediately upstream of the shock, this is supersonic. Immediately downstream of the shock, it is subsonic. And the only possibility that this shock can occur is on the diverging section of the nozzle. Why? Because look at the progression of the flow. You start out from stagnation conditions. This stagnation means velocity equals to 0. And in other words, Mach number is equal to 0. Okay? Mach number equals to 0 means this is subsonic. Because Mach number equals to 0 is less than 1. So therefore the flow starts out at a subsonic flow. Okay? Then in the converging section, it does subsonic acceleration. Okay? When it reaches the throat, it will reach a Mach number equals to 1. In other words, it is at the critical condition. Okay? This only occurs at the throat. After the throat, so downstream of the throat, finally, this is the region where supersonic flow can occur. Okay? You see? So only in the diverging section of the nozzle is where the shock can occur, because prior to the shock, there must be a supersonic flow. And supersonic flow can only occur in here, in the diverging half of the nozzle. Okay? This is for this specific question. Okay? So yeah. The the shock must necessarily occur in the diverging section of this nozzle. Okay? So that's the correct answer for where the shock sits at. Okay. So now we can label this as 1 and 2. Okay? And then based on what they tell us, okay, remember that the shock is infinitesimally thin. So the cross-section area at point 1 is equals to the cross-section area at point 2. So let me write that down. A1 is equal to A2 is equal to 0.0. Let me write this way. 0.0038 meters squared. Okay, so what is the Mach number before and after the shock? Okay, so they're asking me to find M1 and M2. Is there anything else? Yes, so find delta S, okay, the rate of entropy generation through the nozzle if there is negligible friction between the flow and the nozzle walls. Okay, so let us see if we are able to find the Mach number at point 1. And we can, okay? So how do I know how to find the Mach number at point 1? Well, remember what I said. During the flow is being accelerated. And during this acceleration, here the throat reaches critical conditions. Okay, so you must remember from the earlier lectures that for a converging diverging nozzle, critical condition will only occur at the throat. Okay, this is because critical condition must necessarily occur where the cross-section area reaches a stationary value. Okay, where the cross-section area reaches a stationary value. In other words, when dA is equal to 0, and this happens at the throat of a converging diverging nozzle. Okay, so if this is supersonic, then the throat is necessarily at Mach number equals to 1. Okay, so having known that, you know that AT is actually A star. Okay, AT is equal to A star because the throat is already critical, and therefore the throat area is the critical area. Okay, so I hope you understand that much. Okay, so you see, you know the critical area, and you know an area after the critical area, right? You know the cross-section area at a separate point. These two are connected by an isentropic flow. Okay? These two are connected by an isentropic flow, meaning they share the critical area. Okay, so I'm going to use the area ratio formula for isentropic flow, meaning I'm going to use this formula. Okay, so A1 over A star is equal to, yeah, so I'm going to substitute it in. So A1 is this, and A star is this. Okay, then the formula states that 1 over M1 Okay, so how to solve this? Well, you can use your calculator. So let me show you how to do this. Okay, so I want a graph, so I'll click graphs. Then after that, I shall type in that. So on the left hand side, you see 0.0038 divided by 0.0019. Then on the right hand side of the equation, we have the gigantic fraction, right? So you move the gigantic fraction to the left hand side. So you just simply minus away that fraction. The Mach number is unknown, so label it with X. Okay, wait. Yeah. So copy down that fraction. Wait. Uh, four minus- okay, now we plot this. Wait, why is it not plotting? Let me check if I did everything right. 0.0038 minus 1 over x. Wait, I did this wrong. It's supposed to be cross here. Okay, so now we have this graph. Now, we need to find the roots of this graph, right? So, we have two roots here. Okay, sorry. We're finding the 0. We have two roots here. This and this. So which is the correct answer? Is it 0.306 or 2.2? Actually, it's not just 2.2, it's 2.197, okay? So which is the correct one? 0.306 or 2.197? Okay, and the answer is 2.197. Why? Okay, so let's go back here. Okay, so the answer here is 2.197. Okay, why? It's because you see, point 1, remember, is the point that is immediately upstream of the normal shock. And remember what I said so many times already. Immediately upstream of the normal shock, you know that this is supersonic. Supersonic means Mach number is greater than 1. Therefore, it must be the 2.197 and not, okay, not the 0.306. Okay, so you must reject this. Ignore this because 0.306 is subsonic. Okay, so remember, this must be supersonic. Okay, so yeah, that is the value of the Mach number at point 1. So this is done. Now, how do you find the Mach number at point 2? So you see, 1 and 2 are related by the normal shock, right? And remember what I said, once you have the Mach number at point 1, immediately you can find the Mach number at point 2 using the formula that we saw here. Okay, so you simply directly apply this formula. Okay, so go ahead and do that. So if you apply that formula, so I'm going to directly apply that formula. So M2 squared is equal to 2.197 squared plus. Okay, so M2 will be 0.547. And you see M2 is below 1, and a Mach number below 1 means it's subsonic, which is true, right? Point 2, which is the point downstream of the shock, must be subsonic. So yeah, that's correct in that sense. Okay, now, so we already found M2, and then finally we need to find the entropy change. So notice that the flow, right, is actually mostly isentropic flow. Meaning to say from 0 to 1 is isentropic flow. From 2 to after 2, right, downstream of 2 is also isentropic flow. So the only source of entropy change is the shock. Okay, the shock is irreversibility, therefore it is the only source of entropy change. So if you want to find change in entropy, we simply have to find the entropy change across the shock. It's very simple. So there are two ways of doing this, okay? I'm going to show you the long way, and then after that, I'm going to show you the short way, which I will strongly encourage you to use, okay? I'm going to show you the long way to convince you that it's long, and I'm going to show you the short way to convince you to use that way from now onwards, okay, wherever you can see this trick. Okay, so let me show you the long way. The long way states that, okay, first you need to use the Gibbs equation. Okay, so we need to find T2, T1, P2, P1. Cp and R are known because they are just properties of the air. Okay, so Cp has a value of 1004 in SI units. R has a value of 287. Okay, so all of these are known except the temperatures. So let's go ahead and find the temperatures. Okay, so how do we find the temperatures? Well, T1 can be found using the isentropic flow functions, right? Because 0 and 1 are connected by an isentropic flow. So therefore, we can use the isentropic flow function. I'm talking about the temperature ratio. So this one. Okay, so let's go ahead and do that. I'm going to do this very quickly because we are familiar with isentropic flow. Okay, so T0 over T1 is equal to, okay, so we found we're given the stagnation pressure. Okay, and we're given this formula. Okay, so therefore we can find that T1 has a value of 242.906. Okay, so we found T1 already. Now next we find T2. So how do we find T2? Okay, because 1 and 2, okay, remember 1 and 2 are related by a shock, right? I'm talking about these two are related by shock, therefore we use the shock formulas. So you go to the list of shock formulas, and since I want temperature, I shall use this one, right? So T2 over T1 is equal to, okay, T2 is unknown, T1 is the one that we just found. Then the formula for the shock relations states that it's given by this. Okay, so therefore you can calculate T2 to have a value of 450.442. Okay, so T2 is found. Okay, so we found T2. Next, we need to find P1. It's similar to finding T1. So you again use the isentropic flow relations. So P0 is given. Okay. Earlier P0 they told us is this. Okay, and I'm just using the formula that they give. Okay, so you can find P1 to have a value of 97.118 kPa. Okay, so P1 is found, and then P2, again, you can find because 1 and 2 are related by shock, therefore you use the shock function. So I'm talking about this one. Okay, so P2 over P1. P2 is unknown. P1 is the one we just found. Then this is given by 1.4 times the Mach number is 2.2. 1.4 again times 0.547. Good. Okay, so okay, never mind. You can find that P2 has a value of 531.293 kPa. Okay, so we found everything that we need to know to fill up this formula. So let's fill up this delta S formula. Okay, if you calculate this, you should get a value of 132.47. Okay, this is in SI units. Okay, so this method was the long way of finding the entropy change. Is there a shorter way? And the answer is yes, and I strongly encourage you to use it from now onwards. So what is the shorter way of finding temperature, sorry, not temperature change, but entropy change?